In this video, I want to look at some of the number systems that are really important to computer science. I'm sure that all of you are already familiar with binary, and you may feel comfortable with that, but it's important that all of us in computer science have the knowledge of these different number-based systems because they are so important to understanding how data is stored internally and how humans are able to come up with methods to cover the barrier between our human understanding and our human methods, which are mainly decimal numbers, and those that computers like to use, which of course they're binary. And these other ones are kind of in between. We talk about octal and we talk about hexadecimal, and those are just some number-based systems that make it easier for us as humans to write out the information that's stored internally in binary form in a computer. All right, well, let's get started with this. Number-based systems. Now, I've got just a Word document here that I'm going to go through, so I'm sorry I don't have a fancy, colorful, animated type of video, but this is what I have. So let's just go through it and see if we can gain some information. Now, let's start with binary numbers. So with binary numbers, it's good to write out a table, and that's what I'm showing here. So let's scroll up a little bit. And this table at the top is just the power of 2. And as we go across, from right to left, we have the lowest power on the right, and then we just go up. So all the way up to 2 to the 15 in this case. Okay, so this represents 16 different powers of 2, and that could be 16 bits. Now below that, I have actually calculated what the values are that correspond to those powers of 2. Okay, so 2 to the 0, of course, is 1. And if we go 2 to the 4th, that's 16. So each time we move across, we multiply by 2 and we get the next higher number. One of the neat ones here that kind of stands out is 2 to the 10th is also 1024. Now, 1024 in terms of computer science is 1K. So if you're talking about storage that's 1K or 10K or 100K, then actually what we're talking about in computer science is 1024, that nice power of 10 that you see here. We can represent numbers by picking powers of 2 and putting the either a 1 or a 0 next to that value. Let's look at a binary number that is 16 bits. So here is one that's just all zeros except there's a 1 on the right-hand side. So that binary value is the same, of course, as a decimal value of 1. If we wanted to compute that value, and I know this is trivial, if you look at the 1 on the right-hand side here, then we can go to our table up here at the top and we see that the 1 is a power of 2 to the 0. So on the far right side, we have 2 to the 0, and that would give us the power, that gives us the value 1. So essentially, this is 1 times 1 equals 1. Let's go through several examples of binary numbers. Okay, and here again, here's the table. I should have shown you that down here is that value for 1 embedded into the table of values. Now, let's try this binary string. Okay, so we have all zeros except we have a 1, 0, 0, 0 on the right-hand side. If we write that in our table, we have all zeros across here except there's a 1 right there. Okay, I'm going to keep getting that pop-up because that's what Word does, so sorry about that. So here we have the number 1, or the bit 1, set at the column where we have 2 to the power of 3, which is 8. So that gives us a decimal value of 8 for this binary string. Okay, continuing. Let's suppose we have this string. Okay, so now we have all zeros except there's a 1 here. Okay, so 1, 0, 0, 0, 0, 0 on the right side. And if we put that into our table, then we find that we have a 1 where we have the power of 2 to the 5th. So if we scroll back up, we see that 2 to the 5th is the decimal value 32. So this binary string here is equal to the decimal value 32. It's just 2 to the power of 5. What if we have several 1s in our binary string? Okay, so here's an example where we have all zeros, but we have 111 on the right. If we put that into our table, and we have all the bits here, then on the right side we have 1 at the 2 squared location, 1 at 2 to the first, and 1 at 2 to the 0. So if we look that up in the table, then we have 1 2 squared, which is 4. We have one of those 2 to the first, which is 2, and we have one of those 2 to the zeros, which is 1. So we have to add those together. So this string of all zeros in 111, that's 2 to the squared, 2 squared plus 2 to the first plus 2 to the 0, and if you just multiply those out, then we have 4 plus 2 plus 1 is 7. So this binary string is equal to the decimal value 7. A little bit more complicated one. Let's look at this binary string here. So we have combinations of ones and zeros there. So again, if we place those into our powers of 2 table, then we can pick up the values of 2 wherever there's a 1, and we can find the decimal value for that and add those all together. Well, in this case, we have a 1 at the 2 to the 10th, 1 at 2 to the 9th. We have zeros here. We have 1 at 2 to the 6th and 1 at 2 squared. So if you multiply those out and add them together, then 2 to the 10th, of course, we have our 1024. 2 to the 9th is 512. 2 to the 6th is 64. And 2 squared is 4. So adding those all up, we get 1604. So this binary string then is equivalent to the decimal value 1604. Alrighty, so if you are given a binary string, then all you need is this table that we had at the top, and wherever there's a 1, then you pull that number out, and you add all those together, and that'll give you the decimal equivalent. So it's pretty easy to do. If we had, in our 16-bit example, if everything was a 1, then what number would that mean? I mean, what number would that give us, or what number does that represent, is what I should say. Well, in that case, we would have a 1 for every power of 2. So we'd need to add up all of those powers of 2 from 0 to 15. So I'm showing that here. That's all written out in long form down here. And if you multiply those out, then essentially we're just adding up all the numbers in the table that are those powers of 2, the decimal values, and it all adds up to 65,535. So this bit string, which has all ones, is equal to the decimal value 65,535. What that also means is that is the largest number that we could store in 16 bits. That's the largest positive integer, I should say, that we can store in 16 bits. I have included a table just to show you some values, and this goes from a decimal value of 0 all the way up to 127. All right, so I'm showing in these columns, I'm showing the decimal value and I'm showing the binary value. So I didn't want to make the table too big, but this does show 128 values, 0 to 127, and what the corresponding bit string would be if we have 8 bits. Now, in general, if you have a computer that has n bits of capacity per word, then the biggest number that you can store there is 2 to the n minus 1. Okay, so that's an important thing to remember here, the 2 to the n minus 1. That's the largest positive integer you can store in n bits. Let's look at some examples. Suppose we only had 3 bits in our computer, our tiny computer. Okay, well, 2 cubed is 8, minus 1 is 7, and that's a binary 111. So if we only had 3 bits and they're all set to 1, then the largest number we can store is 7. Okay, how about 4 bits? Okay, 2 to the 4th minus 1 is 16, minus 1 is 15, and that would be all ones for 4 bits in binary. Skipping up ahead here, 2 to the 16, if we have our 16 bits that we just looked at, then 2 to the 16 is 65,536. If we subtract 1, that gives us 65,535, which, as we just saw, that's the largest number you can store if you have a 16-bit word in your computer. Most of our computers now have either at least 32-bit words, and in some cases 64. If we have 32 bits, what number do we have that we can put in there? Well, 2 to the 32 is this number, 4 billion and something. And if we subtract 1 from that, then here is the largest number we can store in 32 bits. This is a number you may have seen in your code, in your programming. This number is the maximum positive integer you can store with 32 bits in your computer word. So this number actually has appeared as that in pause number when we did a find operation, but we didn't find anything. This is the number that's returned, so it returns all ones. So there's a little connection to something you might have seen already. But remember, given in bits, the largest positive integer is 2 to the n minus 1. Now, it is tedious to write out all of these binary numbers. It would be difficult if we wanted to write out a large section of our memory locations in binary, and not only that, it would be very hard to interpret. So there have been 2 shorthand methods developed that helps us as humans to understand and to easily write down the information that's in a word of computer memory or computer storage. Okay, so that's what I just said here. So 2 of those are octal and hexadecimal. Let's look at octal first. Now this one really isn't used very much anymore because it's a multiple of 3, and our computer words now are typically multiples of 4, 16 and 32 for example. But let's look at octal. It's one of the important ones that in the kind of the history of computer science that have been used, because there have been computers that have had multiples of 3 as the number of bits per word. So like 27, for example. Well, let's look at this bit string. We have all of those bits. How can we write those down in a more simple fashion? Well, if we take these bits and we group them in groups of 3 starting on the right-hand side, then we can write down a number that represents those 3 bits. So you can see 101 is 5. And you might need to look at our table. If you don't see that immediately, you can go look at the table up above. Then the next group of 3, 100 would be a 4. So we can group our bits in groups of 3, and then we can write down the single symbol that represents those 3. So in this case, 101 is 5, 100 is 4, 011 we have 3, 001 is 1, 110 is 6. So now we've used up 15 of our 16 bits. So to continue this methodology, that last bit's going to be a 0 or a 1, and you could add another couple of zeros on there if you wanted to. And what did I do here? You could add a couple of zeros to make it a group of 3, and then you have your shorthand over here. That would always be a 0 or a 1. So this string of binary bits can be written in octal shorthand as 061345. Now that number is shorter and it's also easier to comprehend. It's easier to understand that number than it is this string of bits. Now, let's go the other way around. Let's suppose you have a number like 745. Okay, if that's an octal number, then it's very easy to get the binary. If we wanted to go back and see the actual ones and zeros, then we go in the reverse direction. Okay, so the 7 is 111, the 4 is 100, and then the 5 on the right is 101. So we can easily convert from octal back to binary, giving us that string of bits right there. So that's why these techniques are so commonly used. It's easy to go from binary to the shorthand and from the shorthand back to the binary. You can also directly convert this to decimal if you want to. Now, we just saw up above that if we have a binary number, we can use powers of 2 to convert that to decimal. If you have an octal number, let's suppose we have 1362, then you can use powers of 8 in order to convert that back to decimal. So regardless of what base you're using, if it's a base 10, then the first digit will be 10 to the power 0. The second one, 10 to the power of 1. If in this case we have an octal, okay, so this represents 8 to the 0 power, 8 to the first power. Over here, that's 8 squared, and that is 8 cubed. So knowing that, we can just write out this 1362 and multiply it by powers of 8. So we have 1 times 8 cubed plus 3 times 8 squared from this 3. Then 6 times 8 to the first power, that's the 6 here. And finally, 2 times 8 to the 0, which we know is just going to be 2. So then if you multiply that out and add them up, then you get this, 512 plus 192 plus 48 plus 2, and that is 754 decimal. We could do the same thing in binary, but you know how to do that now. We could just take that same string of binary that we had up here, and, well, I'm sorry, that's a different number up there. For 1362, then we could get the binary equivalent of that and then multiply out the powers of 2 and then add those all up and we get 754. But if you have the octal, then you don't have to do quite as many multiplies. You only have to multiply and add 4 numbers instead of several others in binary. Now, let's look at a table that I've created, and this shows the binary string, and it shows the octal number, and it shows a decimal. So this goes all the way up to 35 decimal. So here's the string, and again, I'm just showing 8 bits to keep the table short. So 8 bits, that's shown here for the number 35. Here's the octal equivalent, and here's the decimal value 35. All right, so that's just an example. And here is a power of 8 table that I've included. So, of course, 8 to the 0, that gives you 1. 8 to the 1 is 8. And all the way down the line, 8 to the 7 is this big number over here, 2,097,152. All right, so one more example at the bottom here. If we wanted to take this 1,342 and convert that to octal, then we can use this powers of 8 table up here in order to do that. So that's shown here. There's a second technique that we can use to represent binary bits in a shorthand notation, and that's the one that you'll see the most because it is a multiple of 4, and that fits better with words that are multiples of 4 like 16 and 32. So these, in this case, we are going to make groupings of 4 bits instead of groups of 3. So let's take our same binary string that we had just above, and let's now divide that up into groups of 4. Okay, so again, we start from the right side and we divide that up into groups of 4. And then we replace each grouping of 4 with the corresponding number that it represents. Okay, so 0, 1, 0, 1, that's 5. Let's skip that one for a minute. 0, 0, 1, 0, that's 2. 0, 1, 1, 0, that's 6. But this one, 1, 1, 1, 0, that's 14. And we don't have just a single symbol to represent that. With hexadecimal, there are some additional symbols that are brought in to represent numbers that are 2 digits, because we don't want to have 2 digits to represent a value. We want just a single symbol for that. And as you probably know, we use letters for that. So once we get to the binary value 1010, which is 10, we use the letter A to represent that value. So A represents 10 in decimal. B represents 11, and you can see the bit string that corresponds to that. And we need to have those because if you have 4 symbols, that is, if you have 4 places, 4 bits in your computer, then we have seen already 2 to the 4th minus 1. We have 15 possible bit combinations that we can use. So if we want to represent all 15 bit combinations, then we need to add on these additional symbols A, B, C, D, E, and F. So those are going to be part of a hexadecimal number. And this table shows you the binary, the hexadecimal symbol, as well as the decimal equivalent. Now, let's take an example. Let's look at our binary number here. In this case, we have in this grouping here, 1110, we have the letter E. Okay, now we can look back up at our table, and if you don't recognize that immediately, you don't know that that's 14, then you can look at the table. So 1110 is the letter E, and it represents 14 in decimal. So this is the bit string. Here is our hexadecimal symbol, and we know that that is equal to 14 in base 10. But now we have these 16 bits, and we can represent them with 4 symbols, 6, 2, E5. That is a hexadecimal number that represents this bit string. What does that mean in decimal? Well, here is a table I've included. So here the table goes up to 31, and the size of these tables kind of corresponds to how much space I had on the page, so that's why they kind of are a little bit different. But if you get to the number 10 in decimal, then A will be the symbol in hexadecimal, and we always have the bit string shown over here. When we get, say, let's go to the number 26, okay, so that's 1A. Well, what does that mean? Well, okay, so that's 8 to the 0 and 8 to the first, so that's 8 plus, this is going to be 16, I'm sorry, not 8. So that's going to be 16 to the first power, and A is going to be 10 times 16 to the 0 power, so that gives us 26. So this is a base 16 system. Let's look at how we can convert a hexadecimal number to a decimal number. So let's use this example, 2FD6. We want to convert that to decimal. That's a hexadecimal value. Well, we follow the same process, and we need to know the powers of 16 and what numbers in decimal they correspond to. So that table is shown here. Okay, so 16 to the first is 16, here's 16 squared, 16 cubed, and so on, all the way up to 16 to the fifth power. In our example, we have our 2FD6. So we have 2 times 16 cubed. Okay, so that was over here. Then our F, we can just go ahead and write the F. Okay, we don't have to change it just yet. F times 16 squared plus D times 16 to the 1 plus 6 times 16 to the 0, which is just 6. Now we substitute in the decimal value for F, which is 15. And we substitute in the decimal value 13 for D. Now we can do the calculations. Okay, so 2 times 16 cubed plus 15 times 16 squared plus 13 times 16 plus 6 times 16 to the 0, which is 1. And then we add those together, and the resulting decimal value is 12,246. So if you have a hexadecimal value, then you can pretty easily convert that to decimal. The only real trick to this is that we have to replace those letters by the actual powers of values in decimal before we can do the calculations down here. Let's look at this, and let's look at this example going in the opposite direction. And this is all intended just as a shortcut for us humans to represent the binary data in a computer. So there's nothing really magical about this. It's just a shorthand to represent the binary data stored somewhere, either in your computer, on a flash drive, or whatever that might be. If you have the hexadecimal value and you want to see the binary, then you just take each hexadecimal digit and you replace it with the corresponding 4 bits. So 2 would be 0010. Okay, F would be 1111. D 1101 and 60110. So you might need the table to help you a little bit until you remember the bit patterns for A, B, C, D, E, and F. But once you have that, it's easy to go from the hex back to binary. And here's another table that shows some of these. So we have here the binary, the hexadecimal, the octal, and the decimal. So that's a nice table that, again, it only goes up to 31. So then you have seen representations of these various number-based systems. We have looked at binary, octal, hexadecimal, and then their equivalent value in decimal. The only thing that we've considered here in this video is positive numbers. We haven't looked at how to represent other kinds of numbers. We haven't looked at negative integers, and we haven't looked at how to put in real numbers that are floats and doubles. but we'll do that in another video. So we're going to stop at this point and close this video with number-based systems.